Good morning everyone, my name is Prachi. Let's start thermodynamics. Work function Helmholtz free energy and Gibbs function Gibbs free energy. In addition to the various thermodynamic quantities like internal energy U, work W, heat Q, enthalpy H, entropy S, etc. discussed earlier, two more thermodynamic quantities used very frequently in the study of chemical thermodynamics are work functions, also called Helmholtz free energy and Gibbs free energy, collectively called free energy functions. These are briefly described below. Number 1. Work function. This is usually denoted by the symbol A from the German word Arbeit, which means work, and is defined by the function A is equals to U minus Ts, where U is the internal energy of the system, T is the temperature, and S is the entropy. Since U, T, and S are the functions of the state of the system only and do not depend upon its previous history, therefore A also must be a state function. In order to understand the physical significance of the work function, consider an isothermal change taking place at temperature T, then A1 is equals to U1 minus Ts1 for the initial state and A2 is equals to U2 minus Ts2 for the final state, where A1, U1 and S1 are respectively the values of work function, internal energy and entropy of the system in the initial state, and A2, U2, S2 are the corresponding values in the final state. Increase in the function A accompanying the process will be given by A2 minus A1 is equals to U2 minus Ts2 minus U1 minus Ts1 is equals to delta U minus T delta S, where delta U is equals to U2 minus U1 is the change in the internal energy of the system, and delta is equals to S2 minus S1 is the change in the entropy of the system. Now, according to the definition of entropy change, we know that delta S is equals to Q reversible upon T. Further, according to the first law of thermodynamics as applied to an isothermal reversible process, we have delta U is equals to Q reverse minus H max. Minus sign before W has been used to in W max. Minus sign before W has been used to indicate that the work has been done by the system during the change under consideration. Putting the values of delta S and delta U from equation 5 and 6 in equation 4, we get delta is equals to Q reversible minus W max minus T into make Q reversible by T, that or minus delta is equals to W max. Therefore, for a process occurring at constant temperature, the decrease in the work function A is equal to the maximum work done by the system. In fact, it is for this reason that this thermodynamic quantity has been termed as work function. Although at one time it is called Helmholtz free energy, Gibbs function Gibbs free energy. This is usually denoted by G and is defined by the equation G is equals to H minus Ts, whereas H, T, S are the heat content, temperature and entropy of the system respectively. As before, since H, T and S are the function of the state, therefore G is also function of the state of the system only. Hence, for the isothermal process occurring at temperature T, we can write G1 is equals to H1 minus Ts1 for the initial state, G2 is equals to H2 minus Ts2 for the final state. So delta G is equals to delta H minus T del S, where delta G is equals to G2 minus G1 is the change in Gibbs free energy of the system. Delta H is equals to H2 minus S1 is the enthalpy change of the system. Delta S is equals to S2 minus S1 is the entropy change of the system. The physical significance of Gibbs free energy may be defined as follows. Delta S is equals to Q reversible by T. T delta S is equals to Q reversible at constant P. Delta H is equals to delta U plus P del V by definition of enthalpy change. Substituting the values of T del S and delta H from equation 12 and 13 equation 11, we get delta G is equals to delta U plus P del V minus Q reversible, delta U minus Q reversible plus P del V. Now, according to first law of thermodynamics, delta U is equals to Q reversible minus W max. Minus sign before W indicates that work is done by the system. Delta U minus Q reversible is equals to minus W max. Substituting this value is equation 14, we get delta G is equals to minus Wx plus P del V. But P del V is the work of expansion done by the system corresponding to the increase in volume delta V. Hence, W max minus P del V stand for the maximum work other than the work of expansion. This is called the maximum net work available from the process. Hence, we conclude that for a process occurring at constant temperature and constant pressure, the decrease in Gibbs free energy is equals to the maximum net work obtainable from the process, that is the total work minus the pressure volume work or work of expansion. It is because the change in G is a measure of the useful work done that G has been called as the free energy. It may be further mentioned here that it is customary to refer to Gibbs free energy simply as free energy. The designated Gibbs or Helmholtz is added only when necessary for clarity. Variation of Helmholtz function work function with temperature and volume. The work function is given by the equation A is equals to U minus Ts. Complete differentiation of this equation gives T is equals to du minus Tds minus STT. By definition of entropy change, we know that ds is equals to delta Q reversible upon T. Further, from first law of thermodynamics, we have delta Q reversible is equals to du minus delta W, and if the work is restricted to the work of expansion only, then minus delta W is equals to PdV. Putting this value in equation 4, we have delta Q reversible is equals to du plus PdV. Putting this value in equation 3, we get ds is equals to du plus PdV by T, or TdS is equals to du plus PdV. Putting this value in equation 2, we obtained dA is equals to minus PdV minus STT. If temperature is kept constant, dt is equals to 0. Equation 8 takes the form dAT is equals to minus PdVT. B. If volume is kept constant, dV is equals to 0. Equation 8 becomes dAV is equals to minus STTV. Equation 9 and 10 give the variation of work function with temperature and volume. The change in work function for a complete process under isothermal condition can be calculated as follows. For an infinitesimal change under isothermal condition, equation 9 may be written as TAT is equals to minus PdV. For a complete process under isothermal condition, when the volume changes from V1 to V2, we will have delta AT is equals to minus V1 to V2 integration of PdV. Putting PV is equals to nRT, that is P is equals to nRT by V. For n moles of an ideal gas, we get delta AT is equals to minus W max. Variation of Gibbs functions free energy with temperature and pressure. The free energy is given by the equation G is equals to H minus Ts. By definition of enthalpy, H is equals to U plus PV. Putting this value in equation 1, we get G is equals to U plus PV minus Ts. Complete differentiation of this equation gives Tg is equals to du plus Pdv plus Vdp minus Tds minus STT. And in last, the equation becomes Tg is equals to Vdp minus SDT. This is an important expression which gives a change in free energy with the change in pressure and change in temperature in a reversible process. Equation 6 is called total differential equation. If temperature is constant, dt is equals to 0. Equation 6 takes the form dg by dp is equals to v. B. If pressure is kept constant, that is dp is equals to 0, equation 6 becomes dg by dtp is equals to minus s. Equation 8 and 9 gives the variation of free energy with pressure and temperature. The change in free energy for a complete process under isothermal condition can be calculated as follows. For an infinitesimal change under isothermal condition, equation 7 may be written as djt is equals to vdp. For a complete process under isothermal condition, when the pressure changes from P1 to P2, we will have delta GT is equals to P1 P2 integration VdP. Putting PV is equals to nRT, that is V is equals to nRT by P. For n moles of an ideal gas, we get delta GT P1 to P2 nRT by P. dP is equals to nRT P1 to P2 integration dP by P, which is equals to nRT ln P2 by P1. Further, for an isothermal process, P1 V1 is equals to P2 V2. Substituting these values in equation 12, we get delta G is equals to nRT ln P2 by P1. This is the same expression as equation 13 for change in work function. Thus, delta G is equal to delta A. This appears to be a contradiction with the result discussed earlier. However, it may be understood clearly that the quality holds good for an ideal but not in general. Criteria for feasibility and spontaneity of a process. As already discussed, the net entropy change for the combined system and the surrounding can be taken as a criteria for the feasibility or the spontaneity of a process. The result arrived at were: number 1, if delta S of system plus delta S surrounding is greater than 0, the process is irreversible, that is, it is spontaneous or feasible. Number 2, if system plus delta S surrounding is equals to 0, the process is reversible, that is, the system is in equilibrium. The above two results may be combined and put in the form: delta S of system plus delta S surrounding is equal to or greater than 0, where the sign greater than refers to an irreversible process and sign equal to for a reversible process. The above criterion, however, requires knowledge of both delta S of system and delta S of surrounding, which is not convenient. Hence, a number of other criteria which require the knowledge of the change in some thermodynamic quantity of the system only are preferred. This may be derived as follows: for an infinitesimal process, the above criteria may be written as ds system plus ds surrounding equal to or greater than 0, where the sign greater stands for irreversible process and the sign equal to for the reversible process. If the surrounding lose heat delta Q reversibly isothermally at the temperature T, which may be absorbed by the system reversible or irreversibly, then ds surrounding is equals to minus delta Q reversible by T. Further, according to the first law of thermodynamics, delta Q reversible is equals to du plus P dV. Substituting this value in equation 3, we get ds surrounding is equals to minus du plus p dv by t. Substituting this value in equation 2, we get ds system is equals to ds system minus du plus p dv by t is greater or equal to 0, or tds minus du minus p dv greater or equal to 0, where ds stands for the entropy change of the system and subscript system has been omitted. Equation 6 is the basic equation which leads to a number of criterion for predicting the feasibility of a process. In this equation, the sign equal stands for the reversible process and the sign greater for the reversible process. From equation 6, the various criteria may be reduced as follows. Number 1, in terms of entropy change of the system, if the entropy, internal energy and the volume of the system are kept constant, d is equals to 0 and dv is equals to 0, then from equation 6 we have ds is greater than or equal to 0, where the sign equal to is for the reversible process and the sign greater for the irreversible process. The subscripts u and v indicate the constancy of these properties. Number 2, in terms of internal energy change of the system, if the entropy and volume of the system are kept constant, ds is equals to 0, dv is equals to 0, the equation 6 becomes tu less or equal to 0, where the sign equal stands for the reversible and sign less than stands for the irreversible process. This implies that if a process under constant conditions of entropy and volume is accompanied by a decrease of internal energy and the process is irreversible. If no change of internal energy takes place, the process is reversible. Gibbs Helmholtz equation. The Gibbs free energy is given by the equation G is equals to H minus Ts. Hence, for an isothermal process, we can write G1 is equals to H1 minus Ts1 for initial state, G2 is equals to H2 minus Ts2 for the final state. Subtracting equations 2 from equation 3, we get delta G is equals to H minus T delta S. Taking up equation 1 again and putting H is equals to PV u plus pv, we get g is equals to u plus pv minus ts. Differentiating this equation completely, we get dg is equals to du plus p dv plus v dp minus tds minus sdt, and in last we get tds is equals to du plus p dv. Substituting this value in equation 6, we get dg is equals to vdp minus sdt. If pressure is kept constant, dp is equals to 0, so that we have dg is equals to minus sdt and minus s is equals to dg by dt. For the initial state, minus s1 is equals to dg1 by dt. For the final state, minus s2 is equals to dgt by dt. Subtracting equations from 9, we get delta S is equals to dg2 minus dt minus dg1 upon dt. Substituting this value of minus delta S in equation 4, we get delta G is equal to delta H plus T into delta G upon delta T. This is most common form of Gibbs-Helmholtz equation. Starting from with the expression for the function A is equals to U minus Ts, and proceeding exactly in a similar manner as above, the following analogous expression can be derived. Delta A is equals to delta U plus T into may delta A upon delta T. This is another form of Gibbs-Helmholtz equation. Further, sometimes Gibbs-Helmholtz equation is put still in another form, which is derived from the equation as follows. Dividing equation 11 throughout by t square, we get minus delta H upon t square is equals to delta G by T upon delta T. It may be noted that all forms of Gibbs-Helmholtz equation involves quantities like delta G and delta H, which are state functions, do not depend upon the path followed. Hence, Gibbs-Helmholtz equation is a general equation applicable to reversible as well as irreversible process. Application of Gibbs-Helmholtz equation. One of the application of the Gibbs-Helmholtz equation is that knowing the free energy change at any two different temperatures, the enthalpy change accompanying the process can be calculated. However, the most important application of the Gibbs-Helmholtz equation is in the study of galvanic cell, which is briefly explained below. When a redox reaction is allowed to take place in a single beaker, heat is evolved. Earlier, it was believed that when the same reaction is allowed to take place in a electrochemical cell, the electrical energy produced was equivalent to the heat evolved. However, later on it was found that in Gibbs and Helmholtz, by saying that electrical energy produced was equal to the decrease in the free energy accompanying the cell reaction, they pointed out that if the n is the number of electrons given out by one of the electrodes or taken up the other electrode, then the quantity of electricity produced is equals to n farads, where F is equals to 1 farad is equals to 96,500 coulombs. If E is the EMF of the cell, then electrical energy produced by the cell is equals to NEF. Decrease in free energy minus delta G is equals to NEF. Substituting this value in the Gibbs-Helmholtz equation, we get NEF is equals to minus delta H plus TNF d upon dt into P. Thus, knowing the temperature coefficient of the EMF of the cell, that is T by dt, delta H can be calculated if E is known or vice versa. Evidently, the electrical energy produced NEF is equal to the heat evolved only when d by dt is equals to 0. Nernst heat theorem. W. Nernst 1906 made a detailed study about the variation of enthalpy change and free energy of a system with decrease of temperature. The result thus obtained is called Nernst heat theorem, as briefly described below. According to Gibbs-Helmholtz equation, delta G is equal to delta H plus T delta G upon delta T. From this equation, it is evident that an absolute zero, that is when T is equal to 0, delta G is equals to delta H. However, Nernst observed that as the temperature is lower towards absolute zero, the value of delta G upon delta T decreases and then approaches zero asymptote. This means that delta G and delta H are not only equal at the absolute zero, but the values approach each other asymptotically in the vicinity of this temperature. This result is known as the Nernst heat theorem. Mathematically, it may be expressed as graphically. The result may be represented as shown in figure. Delta G has been shown as greater than delta H temperature away from absolute zero. However, the reverse is also possible because delta G upon delta T can be both positive or negative, but we know that delta G upon delta T is equals to minus delta S and delta H upon delta T is equals to delta Cp. Combining these results with equation 1, we get, since gases do not exist at the absolute zero, this means that heat theorem is not applicable to gases. Similarly, it has been found to be inapplicable to liquids also. Thus, Nernst heat theorem is applicable to solids only. Third law of thermodynamics. The result of Nernst heat theorem led to enunciate a generalization which has been called as the third law of thermodynamics. In other words, third law of thermodynamics follows from the results of Nernst heat theorem as briefly explained below. According to Nernst heat theorem, delta Cp approaches 0 at 0 Kelvin. This implies that at 0 Kelvin the heat capacities of the reactants and products become equal. It seems most probable that at 0 Kelvin all substances have the same heat capacity. On applying quantum theory to the heat capacities of solid, it is found that the heat capacities of solid tend towards 0 at 0 Kelvin. Thus, Nernst heat theorem leads to the following result. Also from Nernst theorem, proceeding exactly in the same way as above, it may conclude that all solids have the same entropy at absolute zero of temperature and it tends towards zero at absolute zero of temperature. The generalization is known as third law of thermodynamics. It may be stated as under: the entropy of all perfectly crystalline solids may be taken as zero at the absolute zero temperature. In a broader sense, the law is usually stated as follows: every substance has finite positive entropy, but at absolute zero of temperature, the entropy may become zero, and in fact, it does become zero in case of perfectly crystalline solids. Like the first and the second law, this law is also a generalization based upon experience, and there is no direct proof for this law. However, the law has been verified in a number of ways, and there is no doubt about the validity of the law. It is important to know that third law of thermodynamics does not state that the entropies are zero at t is equals to zero. It merely states that all perfectly crystalline solids have the same entropy at t is equals to zero. Choosing a common value as zero is only a matter of convenience. It is important to mention that whereas first law and second law have led to the development of the concepts of energy and entropy respectively, the third law does not lead to any new concept. It merely places a limitation on the values of the entropy. For this reason, some workers do not think it is appropriate to call it a law. However, like the first and second law, it is generalization which leads to the conclusion in agreement with experience, and hence it is a law in scientific sense. Importance of the third law: evaluation of absolute entropies. The importance of the third law lies in the fact that it helps in the calculation of the absolute entropies of elements or chemical compounds at any desired temperature. This may be illustrated as follows: the infinitesimal entropy change is given by delta Q is equals to Cp dt. Substituting this value in equation 1, we have ds is equals to Cp dt upon T. Hence, the entropy change of a substance when its temperature changes from absolute zero to the temperature will be obtained from the equation St minus S0 is equals to Cp dt by T. Integration limits from 0 to T, where S naught is the entropy of the substance at absolute zero, St is the entropy of the substance at temperature T. Now, according to the third law of thermodynamics, S naught is equals to 0. Thus, the entropy of the substance at temperature T can be calculated from the measurements of heat capacities at a temperature between 0 degree Kelvin to T degree Kelvin. The integral in equation 3 can be evaluated by plotting Cp versus L and T, and then measuring the area under the curve between T is equal to 0 to T. Thus, the evaluation of entropy requires a measurement of heat capacities at different temperatures between 0 Kelvin. However, a problem arises with the measurement of heat capacities at low temperature. For example, in the plot given in figure 3.2 above, the heat capacities along the curve BC are experimental values. The point B corresponding to the lowest temperature after which the experimental values can be determined accurately. To get the complete area under the curve from T to 0 Kelvin, extrapolation of the curve is done as shown by the portion B of the curve. The values corresponding to extrapolated portion is usually found by applying d by third power law for the heat capacities of solid at low temperature, where Cp is equals to AT cube, where A is an empirical constant. If B corresponds to temperature T1, C corresponds to temperature T, And remembering that A corresponds to 0 Kelvin, integral given in equation 3 can be split into two parts as follows. St is equals to Cp by T into dt, limits from 0 to t1, plus Cp by T dt, limits from t1 to t. The value of the first integral can be found by substituting the values of Cp from equation 4. We have limits Cp by T dt integration limits 0 to t is equals to at1 का cube upon 3. Hence equation 5 becomes st is equals to at1 का cube plus 3 plus Cp by T into dt integration limits from t to t1. Further, as Cp is equals to at cube, therefore at1 का cube by 3 is equals to 1 by 3 Cp at t1. This means that the entropy change from 0 Kelvin to T1 and is equals to 1/3 of the value of Cp at T1. Hence, equation 5 can be simplified further to the form St is equals to 1 by 3 Cp at T1 plus Cp by T dt integration from T1 to T. It is important to remember that the calculations described above are applicable only to a solid involving no moleifomorphic change between 0 degree to T degree Kelvin. If some moleifomorphic change is involved in this range, the entropy of transition, where delta H is the molar heat of transition and TTR is the transition temperature, will have to be included in the value calculated above. For liquid and gaseous substance, the total absolute entropy of the substance at the given temperature will be sum of all the entropy changes which the substance has to undergo in order to reach that particular state, starting from the crystalline solid at absolute zero. Thus, if a substance is gaseous at 1 atm pressure and 25 degrees Celsius, the entropy of the gas at 25 degrees Celsius will be the sum of the following entropies involved at different stages. The entropy of the heating crystalline solid from T is equal to 0 to T is equal to Tf, the melting point or fusion temperature. Number 2. The entropy of fusion or fusion delta Fh upon Tf, where delta Fh is latent heat of melting or fusion. The entropy of heating the liquid from Tf to Tb, the boiling point. The number 4. The entropy of vaporization delta Vh upon Tb, where delta Vh is latent heat of vaporization. The entropy of heating of the gas from Tb to 25 degrees Celsius. A. If the substance is solid at temperature T, only first term is to be taken with Tf is equals to T. If the substance is liquid at temperature T, the first three terms are to be taken with Tb is equals to T. If the substance is gaseous, full equation is to be used. If the solid involves a moleifomorphic transition, another term delta TRH upon delta HTR has to be included in the above expression as already explained. Further, the first integral should be made up of two parts as given by equation. The various entropy changes that occur when the temperature of a substance rises from absolute zero may be represented diagrammatically as follows. The calculation of the standard entropy of nitrogen gas at 25 degrees Celsius is illustrated with the data given below. Test of the third law of thermodynamics. Number 1. By calculating of equilibrium constant. The equilibrium constant is related to the standard free energy according to the equation minus delta G naught is equals to RT ln K. The standard free energy change is related to the standard enthalpy change, the standard entropy change according to the equation. Delta G naught is equals to delta H naught minus T delta S naught. Putting the experimental values of delta H naught and calculated values of delta S naught using the absolute values of entropies obtained from the third law of thermodynamics and applying the relation delta S naught is equals to S products minus S reactants. Delta G naught can be calculated for a reason. Putting this value of delta G naught in equation 1, the equilibrium constant can be calculated. It is found that for a number of reactions, the values of equilibrium constant as calculated above comes out to be in a close agreement with the experimental values. Number 2. By comparing with entropies calculated from statistical mechanics. The absolute entropy is calculated on the basis of the third law found to be in complete agreement with those calculated using statistical mechanics. By proving that different allotropies forms of a substance have equal entropies at absolute zero, orthorhombic sulfur changes into monoclinic sulfur at the transition temperature of 369 Kelvin. The entropy of transition delta H is found to be minus 402 joule per mole. Hence, molar entropy of transition will be given by minus 1.09 joule per Kelvin per mole. The individual entropies of the two forms can also be calculated by measuring their heat capacities from T is equal to 0 to T is equal to 369 Kelvin. It is found that hence at transition temperature delta TRS is equals to S naught alpha minus S naught beta minus 1 joule per Kelvin per mole. The elements is perfectly crystalline form are arbitrarily ascribed a value of 0 for the entropy at absolute 0, then all perfectly crystalline compounds will also have 0 entropy at 0 Kelvin, keeping in mind the definition of entropy of formation of a compound. Residual entropy. As explained above, entropies can be determined by applying third law of thermodynamics. These can also be calculated from statistical mechanics or from spectroscopic data. It is found that in most of the cases, the agreement between the third law entropies and those calculated from statistical mechanics is very fair. However, in some cases, the experimental values as found from third law is found to be less than the calculated value. For example, standard entropy is found in third law and calculated from statistical mechanics for CO and N2 are given below. The lower values of third law entropies are explained on the basis that at T is equals to 0 Kelvin, the crystal of these substances are not perfect. That is, there is some disorder present in the solid even at T is equals to 0 Kelvin. The entropy which the crystal of a substance as T is equals to 0 is called the residual entropy. Origin of residual entropy. To understand the origin of residual entropy, let us consider a crystal made up of AB molecule where AB are similar atoms so that the molecule has very small electric dipole moment. Those molecules can adopt different orientations such as AB, 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 AB or AB, BA, BA, AB. Though these agreements or many other random arrangements that the molecules can adopt have very little difference of energy, thus there is residual disorder, hence there is residual entropy at 0 Kelvin. Calculation of residual entropy can be calculated by applying Boltzmann formula. S is equals to K ln W, where W represents the number of possible orientations of the molecules that are equal probable, that is have nearly the same energy, and hence W is called thermodynamic probability and K is Boltzmann constant. A few examples are given below. 1. Residual entropy of CO. Suppose a sample consists of n molecules of CO. Now as each molecule can have two orientations that are equal probable, that is CO, COOC, COOC, OC. Therefore, same energy can be achieved in 2 की power n different ways. That is W is equals to 2 की power n. If hence S is equals to K ln 2 की power n, K ln 2. If 1 mole of the sample is taken, Kn is equals to R, then S is equals to R ln 2, which is equals to 5.85 joule per Kelvin per mole. Number 2, residual entropy of FCiO3. FCiO3 molecule can have 4 possible orientations with nearly same energy. Hence residual entropy is S is equals to R ln 4, that is equals to 11.5 joule per Kelvin per mole. In general, if a molecule can adopt P possible orientations at T is equals to 0, which have nearly the same energy, the residual molar entropy will be S is equals to R ln P. Thank you.